Okay, let's get started. This lecture is about the weak convergence of Markov processes. In chapter 11, we distinguished weak convergence and strong convergence of probability measures when we use the adjoint operator that belongs to a transition function. By the repeated use of the adjoint operator, we get a series of probability measures, and we want to know something about the behavior of this series of probability measures. Especially, we want this series to converge to a unique invariant probability measure. In chapter 11, Theorem 11.12 gave clear conditions under which this series, again generated by the repeated use of the adjoint operator, converge to a unique probability measure starting from any arbitrary initial probability measure at a uniform rate. And this is the point. In strong convergence, we have very definite ideas about the rate of convergence, but forming requirements regarding this rate is too strong. So under weak convergence, we simply drop it. We drop this requirement regarding the rate of convergence. So simply we want the series of probability measures we want the series of probability measures to converge to a unique invariant probability measure. Okay, at any rate, at some rate. We don't form definite ideas regarding the rate of convergence. So the question for the present lecture is very similar to the basic question of the previous lecture: how to define a Markov process so that it has a unique invariant probability measure to which the series of probability measures generated by the repeated use of the adjoint operator converges at any rate. Mainly, this is just a remark in advance. Mainly, we are going to work with finite dimension Euclidean spaces. Practically, it means that we will have L dimension closed intervals. So the state will be described with points, L dimension points, and the coordinates of a point that describes the state are going to move in closed intervals. Okay, in discrete spaces, an invariant measure was defined very simply. If we multiply an invariant measure with the Markov matrix, then we get to the same invariant measure. Okay, this is just a reminder. In the discrete case, a probability vector that describes the distribution of the random variable. So the vector is a probability measure. When the state space is uncountable, we use the adjoint operator. So we have a transition function, and just like in the discrete case, probability measures belong to this transition function, and when we integrate the transition function with respect to the probability measure, the invariant probability measure, we receive the same probability measure. Okay, so this is the way how we define invariant probability measures in state spaces which are uncountable, which are infinite. Okay, mainly the state space, our state space, is going to be finite dimension Borel subsets. Okay, so practically finite number of closed intervals. The first result is Theorem 12.3. When we are talking about the weak convergence of probability measures, we have a number of ways to describe it. So we have alternative but equivalent ways of characterizing, of describing weak convergence. Actually, we have four. I highlighted two of them. The first, as you can see, the first is described in terms of integrals. So we have a series of probability measures. This is lambda n, and this series of probability measures weakly converges to an invariant probability measure. And this fact, this weak convergence, can be described in terms of integrals. When we integrate an arbitrary bounded continuous function f with respect to the series of probability measures, actually this is a series of integrals. This is a series of real numbers. And this series of real numbers has a limit, and this limit is the integral of the same continuous, bounded continuous function f with respect to the invariant probability measure. This is one way of describing weak convergence. The other is described in terms of the probability measures themselves. We have a series of probability measures, lambda n. You know, a probability measure gives values to any set in the sigma algebra, and a series of probability measures weakly converges to an invariant measure when the limit of the numbers, of the real numbers given by the series of probability measures to the same set, so the limit is supposed to be the number that is given by the invariant measure to the same set. There is a condition under which the second statement is true. This statement is true. This statement applies to cases where the boundary of the set A has a lambda measure 0. What does it mean? It seems to be problematic, but trust me, it is not too demanding requirement. First, we need to know what a boundary of a set A is. The boundary of a set A is a zone, is a set of points which are the limits of convergence processes inside and outside the set. So intuitively, we can describe a set in a plane by drawing a line. Okay, drawing a circle. This is a line, and this is the boundary. This line is the boundary of the set, of the circle. This circle line is the boundary of the circle as a shape, because this line contains the points, the endpoints of convergence processes inside and outside the set. The second statement is true only if the boundary of the set A has a lambda measure 0. This is not too demanding a requirement. Please note that on page 71, we defined a probability measure for intervals in exactly the same way which we need. You can see that a probability measure gives the same value to open and closed intervals. Let's have an example. Okay, an very simple and very intuitive example. If we have a continuous random variable, what is the probability? For instance, temperature is a continuous variable. What is the probability that the maximum temperature for today is going to be 26 degrees Celsius. Exactly. This has probability 0 because in any so if it wasn't 0, given that it is a continuous random variable, um, we would have an infinite sum in the end because we have an infinite number of possible temperatures. So any exact point in the state space has a probability 0, so this is not a demanding requirement. Okay, so all in all, weak convergence of probability measures implies convergence of a series of integrals of any continuous and bounded function. First, on the first few pages of the chapter, we work with any state space. Then Theorem 12.5 defines weak convergence for finite dimensional Euclidean spaces. As the next step, we can easily define distribution functions on the basis of probability measures. Probability measures assign values to sets. So if we pick a half-open interval that on the one end reaches minus infinity and on the other end reaches x, this is a set, a half-open interval. The probability measure assigns a value to this half-open interval, and it can be identified as the distribution function that assigns value to any x. Okay. Most importantly, there is a one-to-one relationship between probability measures and distribution functions. Any probability measure defines a unique distribution function, and any distribution function defines a unique probability measure. This is very important because given this one-to-one relationship between a probability measure and a distribution function, we can learn a lot about the probability measure by working with the distribution function. And sometimes it's easier to work with distribution functions, but when we work with distribution functions, actually in the background, we still work with probability measures. The basic property of any distribution function that they are continuous from below and from above. Continuity from below and continuity from above are really similar to continuity in the basic definition of continuity of functions. When we approach a point x from any direction, the limit of the values that the function assigns to these converging points must be the value that the function assigns to the limiting point. Okay, continuity from above is continuity when we approach a point x from above, and continuity from below is the case when we approach a point x from below. Actually, if a function is continuous, then it is continuous from below and from above. And when a function is continuous from below and from above, it is continuous. Okay, this is shown in exercise 12.3. Theorem 12.7 describes the basic properties of f, one of which is continuity. And very soon I will show you some basic tricks, how we can use a distribution function to assign probabilities of a variable falling into a rectangle of any dimension. Okay, we will cover the one dimension and the two-dimension case I think it's really nice. It's pretty beautiful. So I will show you some simple ad hoc examples. Okay. Given that there is a one-to-one relationship between probability measures and distribution functions, the weak convergence of probability measures can be reinterpreted as the weak convergence of distribution functions. Theorem 12.8 is a step along this way. We have a series of probability measures, the series of probability measures lambda n, and we have a probability measure lambda to which this series of probability measures converges, and we have the series of distribution functions that belongs to the series of probability measures, and actually a distribution function f which belongs to a probability measure lambda. The weak convergence of the series of probability measures can be described as the convergence of the related distribution functions in the usual way. In any x where f is continuous, we face the same problem as we faced previously. F can be supposed to be continuous, as Theorem 12.7 declares that f is always continuous from above and continuous from below on sets whose boundaries have lambda measure 0. And we have just covered that when we work with Borel sets, we have sets that have boundaries with lambda measure 0. Okay, the reason is the same as we covered previously. All right. If we work on closed Borel sets, again, in a finite dimension Euclidean space, our state space can easily be described as a series, it's confusing, as a finite dimension closed interval. Okay. If we have a state space which is a closed interval between A and B, it is compact. Okay, it is a closed interval on the real line, so it is compact. And if we have any probability measure mu on this state space, then no wonder it assigns the probability 1 to the case of the random variable falling into the interval ranging from minus infinity up to b, and assigns the probability 0 to the case of the random variable falling into the interval ranging from minus infinity to a. Okay, this is normal. If the state space is the closed interval between A and B, the random variable can only fall into this interval. Okay, so the probability that the random variable falls into the interval ranging from minus infinity up to b is 1. Okay, we can know it for sure, and the probability that the random variable falls into the interval ranging from minus infinity to a, ranging up to a, is 0, because because a is the lower limit, the lower bound, not limit, bound, the lower bound for the random variable. So in this case, the related distribution function gives the value 1 to b and 0 to a. Okay, we have the same result if we define a series of probability measures. So we can easily define in an obvious way a series of probability measures with this basic property. So any series of probability measures that is defined, so the probability measures are defined exactly to this state space, which is a closed interval between A and B, it is sure that the probability measure will assign the probability 1 to the set ranging from -infinity to B and 0 to the set ranging from -infinity to A. And this is what Halley's theorem applies if we have a series of distribution functions with some A and B such that the distribution functions, all the distribution functions assign 0 probability to the lower bound and unit probability to the upper bound, then there is a distribution function that gives the same values to the upper bound and the lower bound, and the series of distribution functions converges weakly to this distribution function. So minimally we can know that there is a distribution function to which the series of distribution function converges weakly, and corollary 1 to Halley's theorem formulates the same theorem in terms of probability measures. It is possible, this is just a reminder, it is possible because there is a one-to-one relationship between probability measures and distribution functions. So if there is a convergent series of distribution functions converging to a unique distribution function, there must be in the background, there must be a series of probability measures converging to a unit probability measure. In this example, which I created, so this exercise is not in the book, I want to shed some light on the content of Theorem 12.7, especially feature D3, according to which we can use the distribution function to calculate probabilities that are assigned to a rectangle. So I'd like to cover the one-dimension and the two-dimension case, and in higher dimensions, the content which we will discover, which will clarify, can be generalized. So these two examples are going to be sufficient, I promise. So one dimension. In one dimension, we are on the real line. Okay, we have an upper bound for the state space and a lower bound and an upper bound. So actually, this is our state space, which is a subset of the real line. What we want to calculate is the lambda measure of this closed interval, and it can be calculated as a difference of two lambda measures. So with the probability measure, we can assign a probability to this interval, and we can assign a probability to this interval, and the probability what we are looking for is the difference of these two probabilities. When we move to 2 dimensions, then defining an interval may seem to be interesting. Actually, this is a rectangle, and this is bordered by 2 points. So actually, this interval, this is an interval in the 2-dimension case, stretched by 2 points, point A and point B. A has 2 coordinates, A1 and A2, and B has 2 coordinates, B1 and B2. It's easy to find the coordinates, the remaining coordinates. This is A1, B2, and this is B1, A2. Yes, B1, A2. Okay, so this is, it may seem strange, but this is an interval in the 2-dimension case, and we want to calculate the lambda measure of this rectangle. This is a rectangle. In 3 dimensions, this is going to be a cube. Okay, so we need to calculate the lambda measure of this rectangle. We can do this directly with lambda, and we can do this with the distribution function. So let's try to find the way how to calculate this probability. Okay, just to be on the safe side, what we are working on is the probability that the random variable falls into this rectangle, into this interval AB. Okay, so when we put the coordinates of point B into the distribution function, we calculate the lambda measure of this half-open interval going from -infinity to B1 and going from -infinity to B2. This is more than we need. So we need to reduce the amount by subtracting 2 additional lambda measures. So we will subtract the lambda measure of this point, and we will subtract the lambda measure of this point. This is okay, but please note that in this calculation we subtracted the lambda measure of this area 2 times, which is more than we need. So we need to add the lambda measure of the point A1, A2. So this is the way how we can use the distribution function to calculate the probability of the random variable falling into the rectangle or the interval in the 2-dimension case. This can be generalized. This can easily be generalized to the 3-dimension case. That's all what I wanted to show you. We still work with L-dimension closed intervals, but so far we have discussed the case of arbitrary sequences of probability measures. We were talking about sequences of probability measures, but we didn't specify how we get them, where they come from. So what if we pick an initial probability measure lambda 0 and let the adjoint operator work to generate a series of probability measures? So this is the case what I mentioned in the introduction. So we repeatedly use the adjoint operator to generate a series of probability measures. This is a series of probability measures, and we want it, not the average, the series of probability measures generated by the repeated use of the adjoint operator to converge to a unique invariant measure. Actually, the problems are the same as the problems we had under strong convergence, and actually under the finite case of Markov chains. There may be cyclical subsets of in an ergodic set, in any ergodic set, and there may be multiple ergodic sets. So let's try to find the minimum what we can expect from a Markov process. So what is the minimum that a Markov process can do? Halley's theorem and its corollaries ensure that if the state space is compact, then there is a weakly converging subsequence of the probability measures. This may be a candidate for an invariant measure, but in the case of cyclical dynamics, it cannot be an invariant measure. We will examine exercise 12.8, yes, in the next slide. So there we will see that when cyclicality is present, then even if there is a convergent subsequent of probability measures, the limit of this convergent subsequence cannot be an invariant measure, only the average. So Theorem 12.10 states this minimum, this very minimum of a Markov process. The series of n-period averages of the probability measures that are generated by the repeated use of the adjoint operator. So the series of n-period averages can be used to define an invariant measure if the state space is compact and the transition function has the failure property. So this is the minimum. Please remember the case of finite Markov chains. So in any case, there we saw that in any case, even if there is cyclicality, even if there are multiple ergodic sets, this series of averages is convergent. So this is the very minimum what we can expect from a Markov process. So we want to find a way by which we can rule out the possibility of cyclical subsets in an ergodic set, and by which we can exclude the case of multiple ergodic sets in this case, because in this case, if we succeed, we can expect the series of probability measures, not the average. We can expect the series of probability measures generated by the repeated use of the adjoint operator to converge to a unique invariant probability measures. We will see it soon that monotonicity of the transition function and the operator t and the failure property are key in finding the requirements by which we can define a Markov process with a single ergodic set with no cyclicality. So this is what we are going to do in turn. Let's have a look at exercise 12.8. Let the state space be this closed interval between 0 and 1, and let's have the difference equation as a law of motion for the state. This is what we are going to work with. In problem A, we need to specify the transition function, which is quite simple. It has two values. It is 1 if s prime, which is 1 minus s, is in set A, and 0 otherwise. So this is the very simple transition function, and we need to show that the transition function p has the failure property. According to the failure property, when we integrate any continuous function with respect to the transition function in this integral, it is supposed to be continuous. The resulting function is also continuous. Okay, that we specified, given the fact that we specified the state space as a closed interval, the integral can be rewritten as an integral on this interval. So this is a tricky integral because transition function p is such that only over 1 minus s it has non-zero value, which is 1. Otherwise it is 0. So what can we know? What can we state about this integral, given the fact that f is continuous? What we know is that the state space in the next period is going to fall into the same closed interval. We can use the transition function to realize that this integral over the interval 0 and 1, this integral, this is s prime, is simple f at 1 minus s, because as we go over the s in the integral, transition function is such that it is going to be 1 only at 1 minus s. So the value of this integral is f at 1 minus s. That comes from the basic properties of the integral, and given that f is continuous, the resulting function mf is also continuous. So we can say that it is true. So it is continuous, so p has the failure property. Okay, in point B, we start working with the special Dirac measure. It is a special measure, it is a probability measure. The Dirac measure assigns the value 1 to any set that contains S and 0 to any set that doesn't contain S. So actually we can use the transition function to define this Dirac measure, you know, the left-hand side describes the probability that given S in this period, state next period falls into the set A. The Dirac measure assigns 1 to any A that contains S prime, which is 1 minus S, and 0 to any A that doesn't contain S prime, which is 1 minus S. So on this basis, we can also define the Dirac measure to point S, which can be interpreted as the probability. If we want to define the Dirac measure with the transition function, it means that the state next period falls into set A. What we need to figure out what the current state is if state next period is S. This is 1 minus S. So if the state is 1 minus S this period, then the state next period is S. Please remember, this is the transition function. So if the state is 1 minus S next period, this period, then the state next period is S. So this is the reason why we defined the Dirac measure for point 1 minus S and S in this way. So let's have a look at this integral. We integrate the transition function with respect to the Dirac measure. And this is, again, a tricky integral. We go over the possible values of S prime from 0 to 1. And the Dirac measure is 0 all along, except at S. So actually, we can use this fact that in the integral, when we go over the possible values of S prime, there is only one value at which delta S is 1. This is S. So no wonder this integral is P SA, which is actually the Dirac measure to point 1 minus S. Okay, so please know that we are using the adjoint operator to receive a probability measure, and when we used this probability measure, we received another probability measure. So delta S as a probability measure cannot be invariant. Okay, so in a more condensed form, we can say that using the adjoint operator with the probability measure delta S, we receive delta 1 minus S. So we received another probability measure, and if we reverse the operation and we use the adjoint operator again, then this can be written, hopefully I am correct. So this is going to be the same probability measure, which is delta SA. So if we use the same adjoint operator one more time, we receive the same probability measure. So what we see is an interesting case when we have different probability measures
for odd and even numbers. So if we want to describe this case in a clear way, we can see that we have distinct cases for even and odd numbers of the use of the adjoint operator. Okay, so this cannot be an invariant measure. This is what Halley's theorem says. We can find a convergent subsequent to which we can find a convergent subsequent, and there is a limiting value to which this convergent subsequent converges, but none of the limits can be taken as an invariant measure, because if we apply these probability measures in the adjoint operator, we always receive the other probability measure, so they cannot be invariant measures. So in problem C, we need to find an invariant measure. So what we have known so far, if we use, let me specify what we know. If we use delta S, the Dirac measure, to point S, then we receive its pair. And on the other hand, when we use the other probability measure, we receive the other probability measure. So according to Theorem 12.10, there is an invariant probability measure, which is the average, which is the linear combination of the probability measures. I will omit the proof. The proof is simple, so we need to demonstrate that this integral with respect to a composite, linearly combined probability measure. So we need to show first for simple functions and then to any integrable function. So it works, trust me. So after a few steps, we receive that this integral is this. So this is a linear combination with the same weights of the integrals. And finally, we receive the same probability measure. So the average of the probability measures is an invariant measure, but please note, in this case we have cyclicality. So we were oscillating between two states and two probability measures. So this is a cyclical case, and in this case only the average can act as an invariant probability measure. In exercise 12.9, we use a dominance relationship between probability measures to infer the dominance relationship between the related distribution functions. So let's start with the definitions. We have two probability measures. So we have two related distribution functions. F mu is related to probability measure mu, and F lambda is related to probability measure lambda. The idea is straightforward. Let's describe the value, the mu measure of this interval as an integral with respect to mu, where the integral is over a monotone increasing function f or something. The first attempt. Okay, we are trying to find an appropriate function which is supposed to be weakly increasing. So the indicator function seems to be an appropriate choice over the half-open interval. So we integrate a function with respect to the probability measure, and actually this is 1 over the integral over the interval, and elsewhere it is 0. So the mathematics works. We can describe the mu measure of the interval as an integral with respect to the probability measure. The only question, there is one question remained: if the indicator function is an appropriate function. Please note that we have this indicator function, and it is supposed to be increasing. So let's try to visualize this indicator function. This is S, and where it is 0, and this is where it is 1. The problem is that if x is increasing, then our indicator function seems to be weakly decreasing. So this function is not appropriate. It is inappropriate. So let's take a second attempt to find an appropriate indicator function, or function in general. The distribution function is in a one-to-one relationship to the probability measure, and it can be described in this way. From S, sorry, it is half open, from S to positive infinity. And in this case, we can find another indicator function over the set ranging from S to positive infinity. Okay, and in this case, the indicator function is appropriate because this is S from minus infinity to S, it is 0, and from S, actually it is open from this direction. So this is 0, this is 1, so it works. It's a weakly increasing function. So yes, it works. And we can do the same. We can do the same with probability measure lambda. So we can find another indicator function, the same indicator function for the probability measure lambda. Without going through the stages we have just covered, we can say that the same, actually, let it be let it be this. I will correct my math in a minute. Okay, so this is going to be it's gonna work. Okay, so we have the same indicator function for probability measure lambda, and because of the dominance relationship between the two measures, it is true that the integral of the two functions with respect to the measures has a distinct relationship. So if we integrate the same function with the domineering probability measure, which practically means that the domineering measure assigns higher values to the same set, we receive this relationship between the integrals from which it follows that we have this relationship between the distribution functions. So from dominance between probability measures, we can infer the dominance between distribution functions. Please note, this is just a reminder to the first attempt, that in the first case, even if I showed you a one-dimension example, in 2 dimensions, the indicator function would also be weakly decreasing. So even in 2 dimensions, in 3 dimensions and the like, we can see that that was the function in the first attempt was not appropriate. So yes, this was just a reminder, a visualization of the indicator function we used in 1 dimension. It can be generalized to any dimensions, and it can be visualized in 2 dimensions. So in problem B, this was problem A. In problem B, we need to walk the same way from the opposite direction. So we want to infer the dominance relationship between the measures from a dominance relationship between the distribution functions. So now we have this dominance relationship between the distribution functions, and we want to know if we can show that this dominance relationship between distribution function implies the dominance relationship between the probability measures. Let's start with the definitions. This is something we have already covered. This is just a reminder. This is how we defined the distribution functions. And the same is true of the distribution function belonging to lambda, probability measure lambda. If this is true of the distribution functions, which is true by assumption, then we can replace it with another inequality. Okay, and from this it follows that lambda is lower, gives lower value to the same interval than mu. This is not dominance. This is not dominance. To demonstrate dominance, we need to show that integrating the same function with the two measures, the integral with respect to mu is not lower than the integral with respect to lambda. To show it, we need to approach function f with a series of step functions. This is interesting. This is useful. This is a useful idea because a step function is a simple function, and given that it is a simple function, we can refer to the fact that a measure, a probability measure, gives a higher value to the same set than the other measure. If we have a simple function fn, then it is true that over the state space it is true. So this way we can translate the dominance relationship between measures into a dominance relationship between integrals. Given the material covered in chapter 7 of the book, the step functions can be chosen in a way that any step function is not higher than a continuous function f. We can refer to the Lebesgue dominated convergence theorem, where the series of step functions converges to the function f, and in this case we can state the following. Please remember that the Lebesgue dominated convergence theorem, with the use of the Lebesgue dominated convergence theorem, we can calculate the integral of a limit function as the limit of the integrals of a series of functions. And it is also true that integrating the same series of step functions with respect to the other measure, we receive the integral of the limit function with respect to the probability measure. And given that this relationship is true, this is true of all n, it is true, finally, it is true that integrating the limit function with respect, so actually what we are using is this relationship, which is true of any n. So finally it must be true of the limit of the series of step functions. So what we see is the dominance relationship of the two measures, which should be demonstrated in the framework of integrals. So we are done. Exercise 12.10 is a short but very interesting and instructive exercise. So I think it's a good idea to pay some attention to this problem too. The state space is a closed interval in the L dimension Euclidean space, and we have three series of probability measures: mu1, mu2, and lambda n. This is three series with of probability measures with a given dominance relationship. So this dominance relationship is true of all n. And we also know that the two probability measures converge to the same probability measure. And what we need to show, what we are supposed to show, that given this dominance relationship between the two, between the three measures, the series of the lambda n probability measures also converges weakly to the same probability measure. The three probability measures define three distinct distribution functions. Okay, so here I am listing the related distribution functions. Lambda, the series lambda n has a related series of distribution functions Gn, and mu, the limit probability measure, it also has a distribution function which is f. Let's use the results of exercise 12.9a. The dominance between probability measures gives a dominance relationship to the distribution functions. So again, by using the results of exercise 12.9a, we know that if this relationship, this dominance relationship, is true of these two measures, then it is true that the related distribution functions are in this dominance relationship, and given that lambda n cannot be higher than mu2 for all n, it follows that this is ugly. This dominance relationship is true of these two distribution functions, all n. So, given the dominance relationship between the probability measures, we have another dominance relationship between the distribution functions, all n. And given the fact that this is true, this applies to all n, it is true of the limit too. So we can say that the limit functions are in the same dominance relationship. And now we can use the fact that mu1 and mu2 converge to the same probability measure. So given the fact that mu1 converges weakly to mu and mu2 converges weakly to mu, on the basis of Theorem 12.8, on the basis of Theorem 12.8, we can say that the related distribution functions are also converging. So there is a limit to this series, which is f, or we can say that distribution function, this series of distribution functions converges weakly to f, and of course, of course, it is also true. So this dominance relationship, this dominance relationship can be rewritten that the two series of distribution functions converge to the same limit. So it must be true. It must be true that the limit of the series of distribution functions Gn is also f. Okay. So the distribution functions of the probability measures lambda n converge to f, but it means that the related measures also converge. So we can say that the series of measures lambda n converges weakly to mu, and this is what we were supposed to show. We are ready.
Let's continue with a definition. A sequence of probability measures can be monotone increasing or decreasing if measures can be ordered in a dominance relationship in a monotone increasing or monotone decreasing sequence. We are going to use this definition. If S, the state space, is a closed bounded rectangle in a finite dimension Euclidean space, and if the transition function is monotone and has the failure property, then the sequences of probability measures that we get by the repeated use of the adjoint operator, these sequences are monotone increasing or decreasing, respectively. We will do an exercise and we will define delta A and delta B as the Dirac measure. This is a special measure, and we will work with the Dirac measures in these exercises. So delta A and delta B in this exercise, and in this slide they are the Dirac measures related to point A and B, the lower bound and the upper bound of the state space. So these series are convergent to an invariant measure, but, and this is the problem, these invariant measures may be different. So the two sequences may converge to not the same measure. This is what we will see in exercise 12.12 very soon, in the next slide actually. Exercise 12.13, to be honest, this is my favorite exercise from this chapter, so I will be happy to dig deeper in this exercise. So exercise 12.13 shows that the compactness of the state space and the monotonicity and the failure property of P, the transition function, are still not enough, are still insufficient to ensure the existence of a unique invariant measure and weak convergence to this unique invariant measure, because there may be multiple ergodic sets. So just like under strong convergence, there may be multiple ergodic sets and there may be multiple invariant measures, just like under strong convergence, and just like in the case of finite Markov chains, we have as many invariant measures, as many ergodic sets. So under strong convergence, we want to do something about it. Under strong convergence, we used condition M, which simply put was the condition under which from any point in the state space we could get to any subset of the state space, which is in the related sigma algebra. Under weak convergence, we will specify a very similar mixing assumption. We say mixing assumption because such a mixing assumption like condition M or assumption 12.1 under weak convergence, so such mixing assumptions ensure that the state can move into the whole state space. So there may be no multiple ergodic sets under such a mixing assumption, because even if okay, so as time is passing by and we have the powers of the transition function, this transition function must be such that from any point of the state space we must be able to get to any subspace of the state space, any subset of the state space. Okay, so this is known by assumption 12.1. We will see it soon that that this assumption is about requiring that from any point in the state space we must be able to get in finite steps to any subsets of the state space. And on this ground, on the basis of assumption 12.1, finally theorem 12.12 shows that if S is a closed L-dimension interval, if the transition function is monotone and has the failure property, and most importantly the transition function satisfies assumption 12.1, then the transition function has a unique invariant probability measure, and most importantly not the average but the series of the probability measures generated by the repeated use of the adjoint operator converges to this unique invariant probability measure. We will have some exercises to dig deeper in this part of the chapter very soon.
Exercise 12.12 is a short but interesting exercise about sequences of probability measures that are convergent, but as we will see, there is no condition in the exercise that would ensure that the limits are the same, so they may converge to two different limits. The probability measure we use is the Dirac measure, which is 1 if A is in set A and 0 otherwise. We will use this equality. So we apply the adjoint operator to the transition function P, where the integral is with respect to the Dirac measure, and it's easy to realize that when we go over the possible values of S, there is only one value at which the Dirac measure is 1, otherwise it is 0. So it is easy to realize that this integral is PAA. Okay, so on this basis we can get to the demonstration. So let's have a function f which is an arbitrary weakly increasing function. Let's use the adjoint. Let's integrate this function with respect to the operator which we received by the use of the adjoint, with respect to the probability measure which we received by the use of the adjoint operator. By using this equality, we can say that this integral can be rewritten in a way where the measure, the probability measure, is replaced with the transition function. And please note that this function is increasing. So this integral cannot be higher for sure. So we pick the lower bound of the state space. Actually, our state space is a closed interval in the L dimension Euclidean space. So this is true. And now that Fa is constant, we can put it in the front, and given that we integrate the probability measure over the whole state space, this is going to be 1, so this is Fa, which can be rewritten as another integral with respect to the Dirac measure. This is a long chain, so let's focus on the point when we integrate Fs with respect to this measure which we received from the adjoint operator. We receive this inequality. And given that the function is the same, given the definition which we find on page 378, this inequality shows a dominance relationship between the two measures. So we can say that this seems to be a weakly increasing sequence of probability measures. So for the case of N1 demonstrated, so if we apply if we integrate the same function with respect to these two probability measures, it shows a distinct dominance relationship. We assume for any n, so what we assume is this relationship So we assume that a similar dominance relationship holds for n, and for n plus 1 we will show that it is also true of n plus 1. We will use this assumption, this assumed relationship, dominance relationship, and we will use Theorem 8.3. So let's do this. We do the same. We integrate this arbitrary increasing function f with respect to the probability measure, which we can rewrite by the use of Theorem 8.3 in this way. So we can reduce n in the operator by 1. And because of the assumed dominance, so because of this guy, it is true. We assumed that it is true. So, by the repeated use of Theorem 8.3, we receive that the same dominance relationship is true of any n. Okay. The weakly decreasing character of the series of this measure can be demonstrated in a very, very similar way. I will show you the first line from which you can proceed in exactly the same way that we took in the previous demonstration. It's very easy. So I will show you the first line if you want to do the other side of the demonstration. So we have the same weakly increasing function. We use the same Dirac measure now with respect to point B, and now we use the same trick. Given that f is a weakly increasing function, by picking the upper bound for the state space, actually this is a constant, and we integrate the probability measure over the whole state space. So this is 1, so this is fb, and if this is fb, then it can be rewritten as an integral with respect to the Dirac measure with respect to b. So now we can see that we found a weakly decreasing sequence of probability measures. So from this point you can perform the same demonstration as we have just done. Now in the second part of the demonstration, we need to show that the two series of probability measures converge to somewhere, possibly to different invariant measures. Given that the state space is a closed interval in the finite dimension Euclidean space, and as such it is a compact set, and given that P has the Feller property, Theorem 12.10 ensures that there is an invariant probability measure. So there is an invariant probability measure because the conditions of Theorem 12.10 are satisfied. Convergence is a different topic. To show convergence, we need Halley's theorem and its corollaries. Given that we use this state space, it is easy to show that to both series of probability measures we have series of distribution functions okay, not A, B, and on this ground, we can refer to Theorem 12.9. So there is a distribution function fa, and there is another distribution function. Okay, we don't need the brackets. To which the other series converges, and these distribution functions belong to the series of probability measures, but these convergence processes are distinct processes. So there is nothing in the exercise that would ensure that the two series of probability measures and two series of distribution functions converge to the same limit. This is exercise. This is exercise 12.13, in which we are supposed to analyze figure 12.4. First of all, we should figure out what it is. It's a policy function. So we can think about this figure as the chart of a stochastic policy function. If we are on the horizontal line, we can find a zone along the vertical axis to which we can get from the current period to the next. Okay, so to any point in the present, we can have zones along the vertical axis. So from, this is S, let it be S1, this is S2. From S2 we can get to this interval along the vertical axis. So this can be interpreted as a stochastic policy function, I think. So we are supposed to show that E1 and E2 are ergodic sets and F is a transient set. I think this is the most beautiful exercise in this chapter, and one of the most beautiful exercises in the whole book. So I think it's important to pay attention to it. So why is it that E1 is an ergodic set? Let's have a look at, this is S1, S2, S3 and S4. From S1, which is the lower bound of the set E1, we can get to this interval, which is in the picture of E1. So this is E1. This is E1. And from S1 we get to a set which is a subset of E1. And from S2 we also get to a set which is a subset of E1, and from any insight point it's easy to realize that we can get to a zone which is in E1. So there is no chance for us to leave E1 starting from any point in E1, and this is the definition of an ergodic set. So E1 is an ergodic set. The same analysis can be applied to E2. So along the same lines we can show that E2 is an ergodic set. F is a transient set. Why? Because from S2, which is the lower bound for F, there is a chance for us to leave F. We can stay in F only if from S2 we get to S2. In any other case we leave F, and in S3, starting in S3, the only way for us to stay in F is to get to S3. In any other case, we leave set F. Actually, from this zone, we can find the zone from which there is a high chance for us to leave set A, and from this set, it's obvious that from this set we stay in F, but there is a chance for us to get from F to this zone eventually, from which we leave the set F. So there is from starting any point in F, there is a chance for us to leave F, and if we once we have left the set F, the interval F, then we get to E1 or E2, which are ergodic sets. So starting in any of the ergodic sets, there is no chance for us to get back to F. So this is the reason why we call F a transient set. As the next part of the exercise, in part C of the exercise, we are supposed to show that if we define two sequences of probability measures, we converge to different limit measures. Let A be S1 and B is S4 to any element in the series of probability measures, the following is true. So this is positive only if, given the way we defined the function in the exercise, what we work with, which is actually, let me have a look at exercise 12.13. This is the transition function. So here we use the definition of the transition function, which gives value to any set A on the basis of its intersection with the lower and upper bound of the interval belonging to any point S. And this is 0 if A has no common part with E1, the first ergodic set. And likewise, it is also true. This is positive if set A, any set A, has any common part with E2, the second ergodic set, and this is 0 if A has no common part with the second ergodic set. This is true of any n. So it is true, it must be true of the limits of the two series. So the two limits, the two limiting measures, assign values to any set on the basis of the common parts of the set with E1 and E2. Given the fact that E1 and E2 are they have nothing in common, so they are disjoint. The two measures for any n cannot assign the same value to the same set. So the two limiting probability measures must be different. The last exercise for the day is exercise 12.14, which is about assumption 12.1. I'd like to show you that assumption 12.1 exactly means that there is a non-zero probability for us to get from any point in the state space to any subset of the state space in a finite number of steps. So this is the reason why we call it a mixing assumption. We assume that P, the transition function, is monotone, and that assumption 12.1 is satisfied by a triple C, epsilon, and n. So there is a C. This is the state space. This is AB. So C is somewhere. Okay. So the fact that assumption 12.1 is satisfied it means that this probability is non-zero, and this probability is also non-zero, and we will use, so these are assumed. Okay, this is important, and we will use these assumptions. All right. So what we need to show that this probability from any S belonging to the state space is non-zero, and this probability in a finite number of steps is also non-zero. So we have two assumptions and one thing or two things to demonstrate. In other words, if assumption 12.1 is satisfied and P is monotone from any arbitrary S in the state space in a finite number of steps, we can get to any subset of the state space, arbitrarily chosen subset of the state spaces. This is what we need to demonstrate. So the state space is a closed interval. All right. And from the fact that P, the transition function, is monotone, the following comes. And please note that this is something we assumed. So we just needed to make good use of the fact that P is monotone. So from any S in the state space, which is arbitrary, with a non-zero probability, we can get to the CB subset of the state space. And the only thing we needed to utilize is the fact that P is monotone. Okay, there is only one thing to demonstrate, the same in the case of the set of the interval AC. This can be rewritten in this way, because interval AC is the complement of CB. So this is true. And from the fact that P is monotone, monotonicity of P means that the following inequality holds, right? Because B is the upper bound for the state space. So okay, we can go on in the same line. So nope. So yes, given the fact that P is monotone, it follows that this is higher than or equal to Pn B CB. This is what we are using, which is Pn B AC, which cannot be lower than epsilon. So we demonstrated what we were supposed to demonstrate.